Hi everyone, I'm Arya. On behalf of my team, I'm presenting our work PiCaZo, Pixel-Aligned Contrastive Learning for Zero-shot Domain Adaptation. Zero-shot domain adaptation is a kind of transfer learning where a model is trained on a source domain and adapted to a target domain without access to any data from the target domain. Here's an image taken in clear weather during daytime, and the segmentation output for this is pretty accurate, whereas for the nighttime image, it is not as accurate. For autonomous driving applications, we have access to daytime images in clear weather. Our goal is to solve domain shifts to adverse weather conditions such as snow, fog, and night, to enhance generalization and reduce the dependence on target domain dataset. Prompt-driven zero-shot domain adaptation. It proposes a framework that uses text prompts to simulate target domain features. PODA takes daytime images from Cityscapes dataset, passes it to pre-trained clip image encoder, and text description for target domains to text encoder. It augments the low-level features extracted from the image encoder to match the target domain description. PODA uses these augmented features for transfer learning on a pre-trained model to adapt to the target domain. The drawback of this framework is that it takes one domain description at once and trains a separate model for each domain. It also relies on phrase-on encoder. Unified language-driven zero-shot domain adaptation. It is a segmentation model that adapts to multiple domains. Similar to PODA, it augments features and uses them for domain adaptation. ULDA performs regional and pixel-level alignment. These align the classes in a particular image in different domains to retain the correlation between the features. The drawback of this approach is that it relies on frozen encoder and does not allow to fine-tune on downstream dataset. Traditionally, domain adaptation requires unlabeled images from target domain during training. But in real-world cases like driving through a snowstorm, it is difficult to have access to dataset of such adverse weather conditions. Zero-shot domain adaptation eliminates the need for target domain dataset. Instead, we train a model on source domain dataset. We then simulate the features of target domain using vision language models using text prompts. Our main objectives are, first, to extract the information from the text description to adapt to the visual source features. Second, to preserve the semantic consistency for the source domain. And third, to extend the backbone for segmentation by fine-tuning the encoder. These are our main contributions proposed in PiCaZo. We start by refining the clip vision encoder using a strategy called volt-bin. Unlike prior methods like PODA or ULDA, we make the image encoder trainable and fine-tune it using visual features. To further enhance the learning for night, which is the most difficult domain, we propose contrastive night vision learning. In the second stage, we adapt the model using two key features. First, we introduce a contrastive domain alignment loss, which aligns features from rain and fog domains, helping the model stay consistent across different weather styles. Second, we propose fog-adaptive contrastive training, which specifically aligns decoder output with fog-style embeddings. Through our experiments, we find that PiCaZo consistently outperforms state-of-the-art models like PODA and ULDA in terms of generalizing to unseen domain datasets. Importantly, we do it without increasing the model's complexity, retaining the original parameter count. As you can see in the plot, PiCaZo achieves the highest score on AC/DC while also improving the performance on cityscapes compared to all baseline models. PiCaZo has two stages. First is the feature augmentation stage. In this stage, our goal is to simulate domain-shifted features using only source domain images and text prompts describing the target domains like night, snow, fog, or rain. We propose two key components, volt-bin and contrastive night vision learning. In volt-bin, we make the image encoder trainable and add a projection layer to project the features of each target domain in the text embedding space. Then there is contrastive night vision learning. We apply pixel-level contrastive learning, which helps the model cluster semantically similar features, especially under night conditions. It pulls together same class pixel embeddings and pushes apart embeddings of different classes. We use hard sampling to focus on difficult examples where class confusion is more likely, which improves the feature separation. This is crucial for night scenes where the visual cues are weak and the class boundaries are blurred. By emphasizing this during training, we improve overall generalization to other domains. So here's what happens. If we follow the diagram from left to right, a source image goes through a clip encoder which extracts features. Now, for each target domain, say driving in fog, we pass the prompt through frozen text encoder and get the target embedding. Pin augments the extracted features for each target domain and passes them through backbone and projection layer. Then, they are aligned with the corresponding text prompts for different styles. Finally, the features are optimized with the segmentation losses and CNL to produce better generalization across domains. Finally, we calculate the overall loss function to optimize both the image encoder and projection head. Moving on to stage 2, which is model adaptation. In this stage, we use domain augmented features generated during stage 1 to adapt the segmentation model. We introduce two key components here: contrastive domain alignment and fog-adaptive contrastive training. The idea behind CDA is to align features from different domain styles, specifically fog and rain, that correspond to the same spatial content in the source image. So, for instance, a region that represents a car in both fog and rain versions of a scene should have similar features in the embedding space. To do this, we project these features using a shared projection head pie and then apply contrastive learning on the features from these two domains, which cluster the similar features together. This loss encourages consistency across domain variants of the same image. Next, we introduce FACT, which specifically focuses on improving the model's understanding of fog domain. We perform contrastive learning between decoder output and fog style features that were generated using prompt embeddings in stage 1. Looking at the diagram, the source image is passed through encoder, followed by the text domain rectifier block. The decoder features, rain, and fog features from stage 1 are passed through a shared projection head pipe. The two losses, CDA and FACT, are applied, optimizing both encoder and decoder layers. I'll quickly summarize the overall training process. In stage 1, the model takes an input image from source domain dataset, passes it through the encoder to extract features. The feature is augmented to end domains. Then we perform contrastive learning on night domain, optimize the features, and store them. In stage 2, we again pass an input image to pre-trained source model and obtain output features. We add our augmented features to it, perform CDA and FACT on rain and fog features. Finally, we optimize the overall loss function and update the adapted model. We use cityscapes as our source domain dataset. For evaluation, we test on three unseen datasets: ACDC, MUSIS, and GTA, each representing different conditions like night, rain, snow, fog, and synthetic environment of a game. PiCaZo shows consistent improvements in all the three datasets, an improvement of 1.87% over the state-of-the-art model ULDA in ACDC, 1.24 in MUSIS, and 1.4 when tested on GTA dataset. In this graph, you can see that PiCaZo outperforms the baseline models across most of the target domains. It achieves a score of 44.47 in ACDC rain, beating ULDA by 2.5. We have also performed some ablation studies. We observed that using CDA, FACT, and CNL together gives us the best overall performance. We also applied CNL across different domains and observed that contrastive learning on night gives us best average performance across all domains. Freezing each layer of encoder showed us that it performs the best when all the layers are made trainable. And finally, PiCaZo outperforms PODA even when we use irrelevant text prompts. Here are the qualitative comparisons. PiCaZo produces much cleaner segmentation masks in target domain and preserves the object boundary better than PODA. To wrap up, I'll highlight the main takeaways from PiCaZo. Our goal was to adapt models to unseen domains like fog, rain, and night without accessing any target domain data during training. We introduced VoltPin, a fine-tuning strategy for clip vision encoder with contrastive night vision learning on simulated nighttime features. This enables the model to learn robust features that generalize well with domain with substantial appearance shifts such as night, even without direct supervision from those domains. For model adaptation, we propose two modules: CDA, which aligns features between rain and fog, helping the model generalize better across unseen weather conditions. And FACT, which specifically adapts the decoder features to fog-specific patterns more effectively. From our experiments, we observed that PiCaZo achieves a higher average MIOU improvement, an average MIOU improvement of 3.6% over the source-only model. It outperforms ULDA by 1.4% and PODA by 1.79% on an average across all benchmark datasets. All of this is achieved without increasing the model complexity. Our framework maintains the same architecture size as the original model. That concludes my presentation. Thank you.